So I'm going to talk on joint work with Richard Bamler, Esther Cabezas Rivas, and Peng Lu. Right, so it's about curvature conditions which, well, yeah, so first of all, curvature conditions which are preserved, like non-negative curvature operator, but then what happens if you have only a lower bound on this curvature condition, right? And then things could be proved in dimension 3 by Miles Simons. He could prove quite a few things, but they were sort of related to the fact that in dimension 3, the curvature operator has a tendency to go to non-negative anyway. And so this is no longer the case in higher dimensions, so one needs sort of a different argument for this, right? So what we are sort of interested is basically, suppose the curvature operator is larger than -1 or minus epsilon, and what happens then if you run the Ricci flow, right? So we want to get some statement on the Ricci flow, right? So maybe, yeah, I mean the main theorem is not so difficult to understand. Maybe I'll start right away with the main result. For all n, there exist, for all n and v naught, there exists a constant c, only depending on c and v naught, such that the following holds. And a t naught, such that the following holds. So if we start with if mg is compact, the curvature operator is larger or equal than minus L, larger than minus 1. And we have some non-collapsing assumptions. So the volume of any unit ball is larger than V naught for all p. Then the Ricci flow exists at least until time t naught. So then the Ricci flow until t naught, and the curvature operator g of t at later time is still larger or equal than minus c times L. And c is this universal constant. That means if L is really small, then afterwards the curvature hasn't gotten much worse. That's sort of the idea. And on top of this, we do have curvature bounds. That's less or equal than c over t. So automatically the curvature, if you flow the matrix, then actually afterwards the curvature will be bounded, right? So by some universal constant. Okay, so yeah, I mean, maybe to sort of try to get you interested, maybe I'll mention a corollary first, right? So one corollary is given n, v naught, and d, there's a epsilon another chalk. Oh, it makes noise, or?
No,
It's not. It's you cannot see it. Oh, okay. Okay. Well, that's not good. Okay. A corollary. Given n d and v naught, there exists an epsilon such that any compact manifold n-manifold with diameter less than d, volume larger than v naught, and curvature operator larger than minus epsilon also admits a metric with curvature operator non-negative. And so the manifolds with non-negative curvature operator, they are classified, right? So the main obstacle was sort of to understand the positive case, and that was done in the paper of Christoph Böhm and myself, right? So so in the positive case, they are just the space forms, and in the non-negative case, well, that was basically done before the rigidity part of it. You can use the strong maximum principle to see that either the manifold is a product or you are on a symmetric space. Okay, so these manifolds are classified, and okay, so and yes, so and there's sort of a general the general question: what are the manifolds with almost non-negative curvature operator? And so they are more general than these, right? So but the basic difference is essentially you don't assume a lower volume bound in general, right? So I guess there's good evidence that somehow manifolds with almost non-negative curvature operator should be much more rigid than say manifolds with almost non-negative sectional curvature, where you at least can do lots of constructions. I mean, you don't have many obstructions either, but yeah, you can do at least more constructions than you can do with almost non-negative curvature operator. So that's yeah, and so at least one can now deal with a non-collapse case, right? So that's sort of part of the program. And then maybe should also mention a conjecture which one might be able to attack now. And it's sort of related to this business, conjecture of Petrunen. So suppose you have a polyhedral space, given a polyhedral space of non-negative curvature. In the Alexander sense, right? So you have a simplicial complex, you put sort of a flat metric on each simplex, and then you ask that at each codimension 2 link, somehow if you add the sum of the angles, that's less than 2 pi. That's basically the condition, right? So then the question is, does there exist a Ricci flow? Does a Ricci flow come out of it? Which for positive times, which is a smooth orbifold, for positive times, with non-negative curvature operator. So the conjecture would be that all these polyhedral space actually carry an orbifold structure, and then even an orbifold structure with non-negative curvature operator, right? And I mean, why is this related? So, I mean, the way you want to prove such a thing is kind of by induction, right? So, your link already by induction sort of has this orbifold structure with a positive curvature operator, and then you want to smooth these polyhedral spaces by a sequence of Riemannian orbifold metrics, and then you hope that you can at least do it maybe so that these assumptions are satisfied. It's of course not so clear whether you can do it with these assumptions, or whether you can keep a uniform lower bound of the curvature operator, but in principle there's some hope that one might be able to attack this. Okay. Yes. So let me make another remark. So there are also some generalization of the theorem. Right. I mean, one can also try to do some more general lower curvature bounds, but I mean, more like integral curvature bounds. But let me maybe not get into this. But there are also other curvature conditions which one can consider. So if C is one of the following cones, so either all curvature operators so that the complex curvature is non-negative. R M of V, comma V bar is larger or equal to 0 for all V in S, O, and C. So that's the Lie, so you complexify the Lie algebra, and V has rank 2. So that's called non-negative complex curvature. That's a Ricci flow invariant curvature condition, and in the compact case, by result of Brendle and Schön, you still converge to a space form, right? So if you have positive complex curvature, then you know what's going on. And okay, then there are some generalizations of this. V comma V bar is non-negative for all V in SO and C. It's the same thing. V has rank 2. And V is nilpotent, so V cube is equal to 0. So that's also a Ricci flow invariant curvature condition, right? So that's called pick 1. And okay, so then you can also consider non-negative isotropic curvature. Then not V cube is equal to 0, but V squared is equal to 0. But I cannot put that one in here because the remark is going to be if we define. One defines can replace the cone R, Rm non-negative by one of these cones in the above theorem. And so, I mean, then it's sort of, one just has to read somehow the equation slightly differently. Here we said it's Rm is larger or equal than minus L. That's maybe not so clear what that means, but you can just say Rm plus L times the identity is in this cone, right? So that's it should be clear that this is. Yeah, I mean, okay, so this, okay, I hope it's clear. I mean, I didn't really say it very well, but so this condition then just means that Rm plus L times the identity is in this cone. So you can look at this condition for any abstract cone, right. Ask the question, what happens if you're close to the cone at the beginning, and what happens with the Ricci flow. All right, so for these two cones it works. For isotropic curvature, we don't have a proof. I mean, one part of the argument still works, but the other part does not. Right, there are sort of two things involved. One is sort of algebraic calculation that somehow the lower bound L sort of satisfies a partial differential inequality, which is sort of surprisingly good. And that part still works, but then we need some other results, like a Harnack inequality in a certain case, and that's not available if you have only isotropic curvature. Okay, so yeah, maybe I actually try to get into the proof. So all right, so let me first look at this algebraic problem. So I have a Riemann manifold and a solution to the Ricci flow, and I define LPT in 0 infinity such that minimal such that the curvature operator at Pt plus L times Pt times the identity is in the cone. And so C can be C is one of the above three cones, right? So C is either non-negative or are non-negative complex curvature, or pick one, right? Okay. And this part you could actually also allow non-negative isotropic curvature, right? So the result would be the same. Oh, okay. Well, actually, isotropic curvature, we can only do it in dimension above 7. But since we don't have any applications, we haven't really tried to do the low dimensions. Okay, so now the one of the important lemmas is important observation is this. So this satisfies an evolution equation, a partial differential inequality. So the derivative of L with respect to t is less or equal than the Laplace of L with respect to t. So this has to be read in the support sense. I mean, it's a function, and the Laplace can have a lower bound. Plus scalar curvature plus n times L times L, n squared. And so what's important here is maybe what's surprising. So for the whole argument, the factor in front of here is really important. So the 1 is sort of the largest constant we can afford, right? So it's much easier to prove this with a 2, right? So then you can actually argue even for an abstract for an abstract cone which is Ricci flow invariant, as long as it contains this cone, you will have this evolution equation with a 2. but we cannot afford a 2. We can afford a 1, but nothing more, right? So that will be important for what follows later. But I mean, the proof of this is a boring algebraic calculation. I mean, it's not. I won't do it, right? So I mean, this is, you just have to look at the algebraic ODE and look at the corresponding equation, right? So I mean, why would you expect that you get such an equation with at least some constant here? That shouldn't surprise you, because the ODE term, right? So the derivative of the curvature operator is given by Laplace r plus r squared plus r sharp. So you have a quadratic term here, and so if the operator is non-negative, then somehow this term is tangent to the cone, and now you perturb it slightly, and you kind of get a linear term, which sort of a linear term which potentially could have the wrong sign, right? So it doesn't look is not tangent to the tangent cone of your curvature condition. But this linear term you can estimate by L times the norm of the curvature operator times a large constant, and this here is certainly larger than the norm of the curvature operator, right? Right, so scalar curvature plus n times n squared L is larger than the norm of the curvature operator, and so it's not surprising that you get an evolution equation like this, but what's somehow surprising is that the constant actually matters. All right, so okay. Yes. So now let's look at the problem, right? So we are in the situation of the theorem, right? So initially we have Rm larger or equal than minus L, and we actually assume this is larger or equal than L naught, larger than minus 1. L naught is some small constant. So we actually prove the theorem only under slightly stronger assumptions, but this is not a problem. As long as the constant is universal, you can just get this old theorem back just by rescaling. That's not an issue. And the only reason we do this is we want to introduce a stoppage rule, right? So we follow the Ricci flow. We look at the solution to the Ricci flow until time t naught, or yeah, let's say t1, it's not the t naught from above, where t1 less or equal than 1 is maximal with, so the curvature operator for all later time is larger or equal than minus 1. Okay, so we actually want to stop the Ricci flow if actually one of the eigenvalues becomes minus 1, or yeah, if you can also look at this. So if this L becomes 1, right? So then we want to stop the Ricci flow, or yeah, and we also want to stop it if the volume of a unit ball becomes small. So initially the volume was V naught, and so if it drops half, then we want to stop the Ricci flow, right? And so the idea is now we look at these sort of Ricci flow. We don't have a priori, we don't have a lower bound on the existence time, but now we want to prove a priori bounds for these sort of Ricci flows. And in particular, we want to show, well, actually, this is not a problem, right? So this constant is actually going to be automatically is not attained at the time t1. And then this has to be attained, or it has to be, the constant is 1, then we are happy. And this is easy to see that somehow the volume cannot drop very fast. There's a result of Petrunen which actually guarantees that. Okay, right, so the aim is now to prove Rmg of t is larger or equal than minus c n comma v naught of L. And then we can sort of, once we prove this, we can choose the L naught such that this constant is larger than minus 1. Okay. At least that's part of the aim. The other thing which we have to do is we claim that for positive times we actually have full control of the curvature operator, and that one can do now separately, right? So step 1, Rmg of t is less or equal than a constant over t for all t0, t1. So we do have universal control on the curvature operator. Right. Okay. So and this is a easy, I mean, a fairly standard thing by now, right? So how do you do this? So look at the suppose not. Then we choose a sequence. Of AI going to infinity and solutions to the Ricci flow such that for some pi, comma ti, the curvature operator and pi is equal to ai over ti. Right, and so you can always choose a ti minimal, right? So I mean, we are on a compact manifold. We look at the first time for each Ricci flow. We look at the first time where this occurs, and then we do a parabolic rescaling, right? So we rescale the metric so that the norm of the curvature operator at this time is 1. Then the Ricci flow goes backwards in time for this rescaled metric until time square root of ai, right? So until a long time, right? And in the limit, we actually get an ancient solution of the Ricci flow with bounded curvature, right? So limit parabolic rescaling plus rescaling and passing to a limit gives ancient solution to the Ricci flow so now satisfying the curvature condition C, right? So originally we had this curvature, we had like the lower bound -1. Because of this rescaling, the lower bound actually in the limit becomes 0, right? So for the limit flow, we actually have the curvature condition we consider. So either non-negative curvature operator or non-negative complex curvature, or pick one, right? Okay, and then there's a separate argument. If the curvature condition is pick one, then automatically, because it's an ancient solution, you actually have non-negative complex curvature also, right? So if C is pick one, then the ancient solution automatically must satisfy the stronger curvature condition, non-negative complex curvature. All right, so and yes, and now what's the catch, right? The catch is that you know one other thing about this solution. The solution has Euclidean volume growth. I mean, it's going to be non-compact, and it has Euclidean volume growth. That's due to the fact that we have here this unit ball that is always is non-collapsed, right? And so all smaller balls are also non-collapsed by Bishop-Gromov. And that means now if we do the rescaling here, then of course that means a very, very large ball still has a very large volume, right? So that means these solutions have Euclidean volume growth. And they are actually, it's a rescaling. Gives ancient, I should say a non-flat ancient solution to the Ricci flow. Okay, and then there's basically a theorem of Perelman that such a thing cannot exist with non-negative curvature operator, and so what he needs is a Harnack inequality, and by Brändli's generalization of the Harnack inequality to non-negative complex curvature, this proof remains valid even if you take one of these other counts, right? So this does not exist. Contradiction, let's just say Perelman, right? So an ancient solution with non-negative curvature operator does not have Euclidean volume growth. Okay, so I guess that is this is not this is not such a surprising result, I would say. The more interesting part of the proof is then the following. On how do you use this equation to get a lower bound at positive times. Okay, so remember again, sort of, it's on the blackboard which disappeared, so maybe I'll write it again. So LPT times the identity is in C, and PT is a minimal non-negative number such that this is the case. That's how it is defined, right? And then we had the differential inequality okay. So, okay, yeah, so the next first trick is sort of stupid. You can certainly do without it. But I want to get rid of this extra term here, as then I don't have to worry about it anymore. Yeah, I mean, the way you can, this term shouldn't really worry you too much because the L is actually bounded by 1 anyway in our situation, right? But if we take a product with S2 of constant curvature n squared for the initial manifold and run the Ricci flow again, we get a better evolution equation. We get dl dt. Of course, each of the factors actually flows then by itself on the one hand, and on the other hand, the scalar curvature actually gets bigger by n squared, and so then this additional n squared eats up this n squared, right? So then we actually get this evolution equation. Okay. Right, and in principle, we are always free to take a product with S2 of constant curvature, and if we prove the result for the product, then we also proved it for the initial metric. Okay, so now, yes, so now we use the maximum principle, right? So of course we also know L of p comma 0 is less or equal than L, which is some small number less than L naught, less than 1. Okay. Right. So now we compare this to the solution of the PDE, right? So where we actually have equality. So L of p comma t is less or equal than h of p comma t, where h is actually the solution where we have equality everywhere, right? Is equal to Laplace h plus scalar curvature times h, and h of p comma 0 is equal to L. Right, so that's by maximum principle. And now, I mean, yes, so often when you use the maximum principle, at least with Ricci flow, you often compare this to the solution of the ODE, where you just forget about the Laplace term. That wouldn't get you anywhere, right? Because the scalar curvature is bounded by 1 over t. That's not integrable, and that means this ODE. Yeah, the comparison with the ODE doesn't do anything good for you, right? But you can certainly still compare it with the solution of this PDE, and you can write out the solution of the PDE using Green's function or heat kernel, and then you can prove estimates for the heat kernel in order to get the desired result. So that's the strategy. Okay, so now h of p comma t we can write down is equal to L times the integral over m, m comma g of 0, and then g of pt q0 d mu of q. And so this is the fundamental solution to this PDE, right? So Laplace pg plus scalar curvature times g is equal to dg dt. Okay. So if q and 0 is fixed, then in the other two variables it's a solution to this PDE, and as t goes to 0, this is converging to the delta distribution, right? So limit t goes to s, g of p comma t comma q comma s converges to the delta distribution. Delta distribution. Okay. Right. So and now one does what one often does in these situations. So one actually views this now as an as in the variables q and s instead of p and t. So in the other two variables, right? So now this is standard calculation. So dg ds is equal to minus Laplace q g p comma t. So if we consider it as a function in the remaining two variables, then it's a solution to the backward heat equation. And so this is where it's important that the factor here was scalar curvature, right? So that the factor here was 1. So only if it's 1 we have a solution to the backward heat equation. If it's smaller than 1, then we still get a additional term plus scalar curvature times a constant times g, but the scalar curvature will come with a right sign. So here, if the constant there would be larger than 1, then it would come with a wrong sign, right? So but here it's now just a backward heat equation, and what's good about this still satisfies a maximum principle, right? So and that's what you need, right? So so the maximum will be increasing in s, right? So and it's a backward heat equation, so you basically solve it backward. So if the maximum has dropped already below something, then you actually you can be sure that it cannot go above it anymore, right? So now what we prove is one now proves that g of p comma t q comma s is bounded above by a constant, say for s less or equal than t over 2, constant over t to the n over 2 times x of distance s pq squared over c times t. And all what's needed for this is actually, so yeah, so the only thing you need here is yeah, I should write it down. So this works completely general. I mean, so this estimate, the estimate on the heat kernel backward heat kernel only needs yeah, so curvature bounds, right? So like Rm g of t is bounded by a over t, and lower volume bounds, right? So the volume of a ball of radius square root of t, comma g of t is larger or equal than t to the n over 2 over a. Right, so that's all it takes sort of to prove this backward heat kernel bound, right? And I mean, once you have that, you're done, right? Because so if I mean, I missed a minus. That's kind of important. Otherwise, you wouldn't be done. Right. So I mean, this is like a Gaussian, right? And this so the typical scale is like square root of t, right? So if you go to square root of t, then this is I mean, you have this constant. So then if you integrate it over this, then the contribution to this integral is basically some constant, right? But then if you double it, then because this actually goes quadratically, then the maximum over outside the ball of square root of 3 drops dramatically, and you can actually easily see that the volume cannot possibly keep up with it, right? So that means that this integral will actually be bounded by a constant, right? I mean, so this implies that this integral gpt q, 0 is bounded by a constant. Okay. All right. So then maybe I say a few words on how to prove this. Right. I mean, the proof is certainly very elementary, and certainly there have been special cases before. I don't quite think this one has been known. Okay, I mean, certainly what is known is GP T over 2. So if you look at the heat kernel like this, so you don't go all the way back to 0, but you actually go back to time T over 2. Then what this corresponds to this corresponds to a Ricci flow with after rescaling. If you rescale this Ricci flow to a unit interval, corresponds to a Ricci flow with bounded curvature on a unit interval, and then everything is true what you want, right? So I mean, then you certainly have some. This is going to be less than c over t to the n over 2. I mean, some other constant, so x of minus t over 2 x comma y squared c over t. And okay, so one important thing is now to note, so we want to do this now if we actually lower this number, right, go down to 0. So what we know from the maximum principle is the maximum is then bounded by C3 over Tn over 2, right? So our maximum is already completely bounded, right? So the only thing it's somehow about how fast does it go fast enough to 0, right? So that's what you have to worry about. And that's certainly something we use a lot in the proof, right? And okay, so now there's sort of a reproducing formula, right? So g of p comma t q comma s over 2, just because it's a linear PDE, is equal to the integral g of p comma t q comma s g of q comma s I should give this now different name, x comma s q s over 2. Right? Okay, so and that's basically so for this you actually do have a Gaussian bound, right? And for this, yeah, so if you start at for s equal to t over 2, you also have a Gaussian bound, and so somehow yeah, and this Gaussian bound is basically always the same, somehow with a uniform constant C3, nothing changes here. And then you just prove the theorem by induction, right? So you just show that you can always take one half of it from before, and then you can prove the theorem. The only thing which you actually allow yourself is to make the constant here a little bit bigger. Yeah. So okay, there are certainly some details involved, but it's the overall technique is very simple, right? I mean, because you don't have so many assumptions, there's not much you can use, right? So I mean, I guess to some degree the proof is elementary, right? Okay, well, thanks. Maybe I stop here.